Okay, good afternoon, good morning, or good evening, wherever you are. Well, welcome to our seventh ML4LM webinar. And today we have Dr. Nina Raoult as a speaker. The expertise of Nina is at the crossing of the data-driven and process-based land modeling. And in her presentation, she will talk about bridging the physics and data gaps through the parameter estimation and emulation of the land surface model with machine learning. Nina is a research scientist at ECMWF, specializing in land surface modeling, parameter estimation, and machine learning. She's currently involved in the Destination Earth initiative, developing a data-driven Earth system model. And her previous experience includes an ESA CCI fellowship at LSE in France and the Marie Curie fellowship at the University of Exeter, where she worked extensively with a range of observational product and land surface model. And in 2024, she was awarded the Royal Society Fellowship, but fortunately for us, she joined the ECMWF instead. She's a core member of the team leading the land calibration model intercomparison, the CalMIP, and led the community paper on machine learning for parameter estimation in land surface modeling. So, yeah, before I give you the floor, just to mention that this webinar is being recorded. And for the discussion, please put your question in the Q&A section. The floor is yours, Nina. Thank you.
Thank you very much. So I'm going to be talking about primarily parameter estimation, actually, in land surface models using machine learning. But at the end, I'm going to talk a little bit about the work we've been doing also to emulate land surface models. But yeah, a lot of my background is parameter estimation. And I like to start off with this figure on the right, because I think it really encapsulates the problem we have with our parameters in the land surface models. It's quite an old figure, but it kind of captures the kind of idea. Here, a land surface model has been run with a perturbation of different parameters. All these parameters for the land surface have been perturbed within their range, realistic range of uncertainty. And what we see is by projections by the end of the century, we get a spread which is wider than running the model under different scenarios and wider than into comparisons with other models. So to get reliable projections of the future, we really need to reduce this parametric uncertainty. So I've actually worked with quite a few land surface models, and so the results throughout this presentation kind of come from each of these. These are the Joules land surface model, which is part of the UK ESM, the Orchidée land surface model, which is one of the French land surface models, and the ECLand, which is the in-house land surface model at ECMWF, formerly known as HSL to some of you. But what these have in common is they're relatively complex land surface models, and they have a lot of processes. They solve the energy, water, carbon, and nitrogen budgets. I know we've seen this slide many times before, but I think it really captures where we are with land surface modeling. In the 70s, we were very much using land surface models as a lower boundary condition to the atmosphere. But over the decades, land surface models have become very complex and standalone models in their own right, modeling a wide range of processes. The thing is, every time we add a new process, we add new parameters. So we're increasing the parameter uncertainty. So this gives us motivation to try and reduce this uncertainty. And a final slide for the motivation. This is a study using the Joules land surface model, where we took a version of the model and we compared just calibrating the model to observations, here FluxNet data, or doing a structural change, moving from a big leaf to a multi-canopy scheme and doing a bit of hand tuning and seeing how the performance compared to each other. And I think the message is that we can actually start getting really good performances just by calibrating models. We don't always need to go into making the model more complex. Just by reducing the parametric uncertainty and getting the right parameters, we can start fitting the observations better and having more confidence in our projections. The way we do parameter estimation in land surface models, especially the complex ones, is we tend to use a data simulation framework. And by this, I mean a framework which allows us to take model and observation errors, and as well as errors on our parameters themselves. So we have some prior knowledge about the parameters, and we kind of keep that when we do our estimation. And at the end, we're not just looking for a set of parameters that gives us the best fits, but a reduction in the parametric space itself. So we get a reduction in posterior errors. And this is why we try and use a data assimilation framework to do so. Before doing that, we need to select which parameters we want to optimize, calibrate. And to do this, first, we do what's called sensitivity analysis. But before I go into that, I'm going to take a step back and say, what do I mean by parameter? And by parameter, I mean constants in the model. And they can touch different processes. So here I've got some examples from the water, carbon, and energy budgets. But what's really important is that they are fixed. They are fixed in time, they're invariant. And this means instead of trying to correct our parameters at each time we get an observation, which is what's done in traditional data assimilation, data estimation, we're interested in looking over a full window, so multiple years of data to make sure that the parameters we find are unique and they capture seasonal or inter-annual variability. So I said, the first thing we want to do is select our parameters and do a sensitivity analysis to make sure that we're going to calibrate parameters that actually have an impact on our outputs. But the first step in this is even before we do a sensitivity analysis, we need to figure out which parameters we're going to look at, because these models can have hundreds of parameters. And that's not even going into the fact that some of them are also going to be spatialized. There's going to be different values based on vegetation type or soil type. And so we can't do all the parameters at once, and we need to start with a subselection even when we do the sensitivity analysis. And for these parameters, we also need to find a min and a max value, the values of which we're going to vary them. And this is quite an arduous task. And I've given here examples of different land surface modeling communities where we've tried to basically have a spreadsheet where we start looking at what the min and the max values are for different parameters. I wanted to highlight especially the work that's been done with the community land surface model, CLM. There's a paper led by Daniel Kennedy where it just it documents this big effort that's been put into documenting all these parameters and getting them in and the max before being able to even get to the point of doing a sensitivity analysis. So once we have the parameters we want to look at, we can do different methods to see what impact they have on our outputs. This is an example from Orchidea using the Morris method. And this method is quite simple. It just gives you relative strength of the different parameters. But the reason I wanted to show this example is because it kind of shows that the sensitivity will very much depend on where we are globally and what we're looking at. So the bottom left-hand triangles show the sensitivity to land surface temperature. These go from white to black, passing through red. And then the upper right-hand triangles are the sensitivity to soil moisture. And this is passing through blue. And what we can see is in the top bit of the panel where we're looking at just bare soil sites, it's very much the bare soil albedo that's going to control surface temperature. And this RS, which is the bare soil resistance to evapotranspiration, which is going to control soil moisture. But then when we start looking at areas which have vegetation, we start getting more complex interdependencies between the different parameters as there's more processes occurring. And we see specifically N, which is N of the Wankel-Newton equations, gaining importance compared to the other parameters. So it's important to think about where we're going to do our sensitivity analysis and what we're actually trying to target. Another method is called the Sobel method. This is more complex because it lets us also look at the interactions between the parameters. And this figure is quite nice because it shows us that the model is doing what we expect it to do. So each bar is showing each parameter's impact on GPP, photosynthesis. And the left-hand column is over a broadleaf forest site. And what we can see is this kind of gold color is the most sensitive parameter. And this is the one VC max controlling photosynthesis. When we move to a boreal needle-leaf forest, we can see that it's the green parameters which are more important. And these are the phenology parameters. And we're actually in the light-limited regime. So this makes sense that for photosynthesis, it's going to be important to have the right-sized leaves to absorb as much as possible in this light-limited area. And finally, when we move to a semi-arid savanna site, where we're more water-limited, this is where we see that the water parameters, the blue parameters, and the soil hydrology parameters, the purple parameters, are gaining importance. So even before we do any parameter estimation, this can give us a good idea that our model is doing the right thing. However, these methods can be quite costly. We're looking at about 100 model simulations for Morris, order of 10,000 for Sobel. And so naturally, this is one of the examples of where we can see machine learning emulating parameter space is really going to help us. So once we pick our parameters, we're going to put them into a cost function and minimize that cost function. And this cost function takes a difference between the model at a given set of parameters and the observations. And this can be anything from in situ, satellite data, anything we want to minimize the fit. And we also have our background terms, so keeping a prior knowledge about the parameters. And to minimize this cost function, in general, there's two approaches that we use, gradient-based descent. So basically rolling a ball down a hill to see where the minima is, or we can use ensemble methods. And these are going to explore space more thoroughly, but can be more costly because we need more simulations. If we have the derivative, and this is normally through the adjoint or tangent linear, we can also extract information about sensitivity of the parameter locally using this information about curvature of parameter space. And here we can see for this parameter that we've got quite a steep cost function around the parameter. So we know that this is a highly sensitive parameter, and this is a good range for this parameter to be varied between. And they don't have to be 1D, we can also look at a 2D representation. However, for land surface models, especially the complex ones I've been talking about, it's very hard to have this information. The adjoint or tangent linear are very hard to maintain. And this is because these models are community models, which are always evolving with new processes being added all the time. And even though there is automatic differentiable software, which can help us get the tangent and adjoint linear, and adjoint, even before we feed it into the software, we need to get to a point where we have a clear mapping between the inputs and outputs. We've smoothed out all the if statements. There's a lot of work that needs to be done even to become compliant with automatic differential software. And so actually a lot of methods, other methods are being used, such as finite differences or 4D Anvar, which is an ensemble method to approximate the gradient. I won't go into that there, but there's a couple of papers if you want to check out that method. But as we move to more of a machine learning world, if we are able to emulate land surface models with neural networks, then these are automatically differentiable. So we get the tangent linear and adjoint for free. And Pierre Gentil gave a great talk last time talking about what you can do with a differentiable land surface model. The other thing we can do is use large language models to help us translate these land surface models that tend to be in Fortran to more friendly languages such as Julia and JAX, which will help us be more differentiable and also use GPUs for faster exploration of parameter space. But I said, if you don't have the gradient, the other thing you can do is use ensembles. And this is an example using the genetic algorithm, which is an ensemble method, and comparing it to the gradient-based method for 16 first guesses. So trying at 16 different points around parameter space as initial values and seeing where we converge. And we can see generally that the genetic algorithm is outperforming gradient-based descent when we take the median. And that spread is also much smaller compared to the gradient descent method. However, we do have a problem with equifinality. And this is the concept of when we're minimizing the cost function, we can find sets of parameters, different sets of parameters, which gives an equally good fit to the observations. And this is an experiment where we start with 200 first guesses. And we can see that we're getting behavior in our parameter space that we're not going to be able to really capture with Gaussian approximations of space. Especially here, we've got, for example, two nodes happening, or this kind of banana shape. But yeah, the main thing with equifinality is that we always need to have independent data to validate against. So we can't just do our calibration, but we always need to make sure that then we test it against other data sets to make sure that we get the best value possible. So let me give you a few examples of parameter estimation in action. So in general, I kind of see three ways that parameter estimation is used. The first is to derive an operational set of parameters. The second is to help identify structural uncertainties in the model. And then the third is to propagate the uncertainty through a system. And in the interest of time, I'll just tackle the first two. So when we're trying to find an operational set of parameters, this can be very challenging, especially for land surface models, because the land surface is so heterogeneous. And so one of the approaches we've been using a lot is to not just calibrate our parameters at a certain location, but group parameters of a shared trait and optimize the parameters over that shared group. And most of the time, that's plant functional types. And as we can see here on the left, this shows us for one site that if we just optimize parameters for that local site, we get this orange bar, that's the best fit. But if we do this kind of multi-site optimization, we also get something that's comparable. Whereas if we take parameters from other sites, we're not guaranteed to improve the fit. The other thing we can do is pick some pixels that we think are going to be representative. But this can be quite tricky because you're going to need a lot of filtering to find ones that really capture what you're trying to optimize. This leads us also to the question of, like, if we are looking at things like plant functional types or vegetation types, is that enough to really represent the heterogeneity of the surface? So one of the approaches that's been used at ECMWF to get some operational parameters is to use clustering. And this cluster is based on errors of sensible and latent heat flux, as well as vegetation type, soil type, and climate. And by clustering, here with 30 different clusters, we can see that the predictors are mainly the errors in the different fluxes that we're going to be calibrating against, but we also get a map of things that are recognizable in terms of climate and vegetation zones. And then using these clusters, we can subsample a few sites and then run the optimization for that to create new parameter maps. So here we can see how one of the parameters in ECLand, the skin thermal conductivity, before was a very homogeneous map. After doing the clustering approach to calibration using sensible and latent heat flux, we get more of heterogeneous, more like a pattern over the map. We can feed this into the model and we can see we get much better behavior against our observations. And because ECLand exists in a couple system, we also need to see how it impacts atmospheric scores. And in this example, the 2 meter dew point is improved in some regions or very slightly degraded, but the scores are generally quite good. So in this way, we're able to find a set of parameters that we can then feed into the model and use. But I said the other thing that I find quite interesting about parameter estimation is that we can use it to identify structural uncertainties in the model. And this is an example with the Orchidea model, where calibrating against methane fluxes. And here we optimize single site again, so each individual site, and then multi-site trying to find a general set of parameters that works across all sites. And the fact that we can't find a set of parameters that works equally well for all sites means that there's different behaviors happening in the sites that can't be captured just with one set of parameters. And then when we plot it like this and we see that we get different behaviors with increasing methane emissions, especially when we have high methane emissions, we can see that there's actually not enough carbon available at this end. And so that's actually pointing to a structural change that we need to make in the model to make sure that we have enough carbon available for it. And just fixing the parameters is not actually going to be doing that. It's not going to help us do that. Another example is when we calibrated snow albedo over Greenland. For this calibration, we calibrated over the whole ice sheet to find a set of parameters which would help get the albedo better. And we can see that we fit the observations a lot better after our calibration. So we've got our prior in blue and our post in orange. But then when we look at other parts of the snow dynamics, so the surface mass balance, runoff, and sublimation, we can see that these are all degraded with this new set of parameters. And so there's a disconnect between what's happening with the surface albedo and the other processes of the snow ice model. And this led us to look more closely at the snow model and moved from just a few layers of snow model to a multi-layered snow model. And we were able to then capture the behaviors a lot better. So there's a feedback between parameter estimation and model development, which is very key. But yeah, so now I'm going to talk a bit more about how machine learning is going to help us with all these traits. And going back to the figure I showed earlier of the kind of data simulation workflow that we use to estimate parameters in land surface models, It's quite clear that machine learning is really going to help us at every step of this, either through just emulating the model output better or helping us get the right kind of algorithms, helping us get data which is bias-free or gap-filled. And so what I'm going to talk about a little bit is how we use Gaussian processes in particular. And what's good about Gaussian processes is that they give us uncertainty. And so we can use this uncertainty to know how good our emulator is at different bits of parameter space. So a Gaussian process emulator has a mean function and a kernel function. And it's trained by looking at different points. And as you can see, when it has a point of training, there's no error, but in between, we're going to have quite a large envelope of error. But this we can feed into our parameter estimation systems and use that to calibrate our parameters. And remember, there are kind of two ways that Gaussian processes are used in parameter estimation. The first one is what's called machine learning. And this uses a kind of implausibility metric, which is the distance between what the emulator is predicting and the target metric of choice, and also takes into account the uncertainty of the emulator and the error that we have in our model and observations. And the way that history matching works is that we define our parameter space. Again, we need to have our parameters and our prior ranges to have this space. And from this space, we can sample a number of points. Normally, this is 10 times the number of parameters. We can also have a set of metrics that we're interested in looking at, and this can be the RMSE, but it equally could be the amplitude of the time series we're interested in, or a slope at different seasons. And so for each of our model runs, we can compute the metrics, and then we can compute an emulator for each of these metrics. Using these emulators, we can then go on to sample parameter space, taking 10,000 samples, and then these can be used to rule out, using the implausibility metric, that distant metric, things that are incompatible with our targets. And this method, we end up with what's called the not ruled out yet space. So it's not the parameters which are the best, it's the ones that we've gotten rid of and the ones that are left which have not been ruled out yet. And we can do this many waves until we're happy with the space that we have at the end. I'm going to illustrate this using a twin experiment. So this means that we know what parameters we're trying to achieve at the end, but we have added a little bit of noise to make it not completely perfect. And in purple, we've got the prior ensemble. So when we just perturb the parameters within our range of uncertainties, we get this large envelope, and we want to reduce that to have a better fit. And I said what's good about history matching is that we can start to target metrics that we're really interested in. And here, the example we're going to be calibrating, we'll try and find the parameters for net ecosome exchange and latent heat. And we know that the parameters are going to affect things like the amplitude, the slopes, and the initial carbon stock. So these are the metrics we can pick and put into our history matching framework. And if we do several waves, we can start ruling out bits of parameter space which are incompatible. And that's what we've done here. The red areas are the bits that we've ruled out. These are parameters that can't, parts of parameter space that aren't feasible. And in green is where it's most likely. And as you can see, the dot, that's our initial parameters, because we know which parameters we're trying to recover. They exist in this not ruled out yet space. So we've done a good job of finding those parameters. And then if we look at running an ensemble using parameters in the not ruled out yet space, we're a lot closer to the observations than when we were with our initial ensemble. And then I wanted to use this example because it goes back to the figure I showed earlier, where we can see that we're getting kind of a similar pattern in our not ruled out yet space to what we were getting by running our optimization using 200 different prior values. So a lot less costly using emulators to explore parameter space, but we're getting the same kind of behaviors at the end, which is very reassuring. And then this is an example with real data. So the same site as before, but using actual data and more parameters. And what we can see here is that we are reducing the RMSE quite a lot for both the carbon flux and the latent heat flux. But there are bits that we are not able to capture no matter what we do. And so this is where history matching can really help us be a tool for uncertainty quantification. It can help us here. Maybe we don't have the right parameters, maybe we don't have the right parameter ranges, or there's a process that's missing, which means that we're not quite capturing the sync, and especially not the behavior that's happening in autumn as we come out of the sync. So I said there's two approaches, and the other approach is for using Gaussian process emulators is to use the Gaussian process itself to do the optimization. So if we can get the best possible Gaussian process and minimize that to find the set of parameters, then that's the parameters that we can use. And to do this, we use an acquisition function. The example here is expected improvement. And it also still uses the emulator uncertainty and the prediction of the emulator, but also it uses the best estimate we have so far. And sometimes we try and see if whether we want to stay near our best guess or we want to go further away. And this is what the jitter parameter does. So a similar framework to before, but instead of having one emulator per metric, we actually have one combined emulator because we're trying to get the one best possible emulator. And this we can minimize to find us our best set of parameters. And if we want to do more iterations, this is when we use the acquisition function to keep improving parameter. I don't know if you've noticed, but I've got a little figure in each case. The first in history matching, I had a little mouse that was nibbling away at a block of cheese. So it's quite, the idea is to show it's quite conservative. We're just getting rid of little bits that are incompatible parameter space. This method is a bit more aggressive. So if I've gone for, ball in the china shop, just like targeting very quickly, it's less concerned about the errors in the model and the observations. It's just trying to find the best set of parameters given the system that we have. So how does this look in practice? So again, we have our Gaussian processes. Here, observations, so where we've run the model is shown in red. And using our acquisition function, we can see the blue points are the where we should explore next, because this is where we have the highest uncertainty. And as you can see, as we go through the iterations, our Gaussian process emulator becomes more and more sure. And then once we are happy with the Gaussian process emulator, then we can use it for minimization. And I said we've got this little jitter parameter, and if it's small, it allows exploration. So we're saying we're not quite happy with where we are in parameter space. We want to keep exploring. Whereas if it's high, it's what we call exploitation. It's going to exploit the area around the best set of parameters we have so far and try and get the best emulation of that parameter space around that parameter. And this is the approach that we use at ECMWF. And we use it using Quaver scores. So these Quaver scorecards are a heart of ECMWF's development chain. There are these cards on the left where the general idea is if it's blue, it's good, and if it's red, it's bad. But it takes into account loads of different regions. It's quite small, I apologize, but you can see there's the Arctic, Antarctic, Southern Hemisphere, tropics, Northern Hemisphere, and different observations, 2-meter temperature, wind. And it makes sure that any change that you do to the model doesn't degrade this card. So you want to keep it as blue as possible, at least as neutral as possible. And so we can use this as our metrics, combine these metrics together, weight them however we want, and make sure that we have an emulator that is able to give us the parameters, which is going to give us the best output that will give us this best scorecard. And this is just looking at a few of the parameters we've been tuning, just one iteration, but you can start to see some behaviors where we can see some parameters we're going to be able to constrain quite easily and others which are not that sensitive to the metrics we're looking at. And this leads us more to emulating the land surface in general at ECMWF. So a little bit different, leaving parameter estimation for now. But as you might be aware, the ECMWF now has a data-driven weather forecasting system called the AIFS. And this is based on, trained on Error 5 data and then fine-tuned operational data. And it's predicting the next 6 hours ahead using quite a complex architecture, encoder, decoder, processor, decoder, graph attention. And it's all coded using Anemoy, which is a community open tool if anyone wants to play around with the different tools that we're using to develop machine learning models at ECMWF. But the reason I want to talk about it is that there are land surface variables which are included in the IFS. And we have representation of soil temperature and soil moisture of the upper levels. And they do look quite promising. You can see, for example, with the soil temperature that we can see the sun is going across. And in the next version, we're looking to add snow cover. And our early experiments have shown that adding snow cover, we're actually getting better behavior than the physical model itself. And this is because by training on error 5, which has observations ingested, we're correcting some of the errors in the physical model. And then separately, as part of Destiny, we're trying to build a more wider Earth system model. So not just the atmosphere, but looking at different components. And one of the things that we've been experimenting with is whether it's better to have several individual ML models that we then couple, or whether we learn everything at once. And we can kind of think of the AIFS as jointly learnt already with the land surface variables. But if we want to start bringing in the oceans and more hydrology, maybe we also want to focus on more individual models. And so for the land component, we've been developing a standalone emulator called AI Land. And compared to the structure of the AIFS, we've gone for a much simpler structure using a multi-layer perceptron. Because we don't need as much of the information, we don't need all of the graph structure that is in the AIFS, because land surface models, a lot of them don't have lateral communication between grid cells, so we can exploit the fact that they are a column model and train and use every single data point as training. This means that our model is resolution agnostic. We can also train it over certain areas and verify it over different area somewhere else. And it also means that we're going to be able to ingest observations quite easily. And so, yeah, this is the architecture we've been using on the right. And then at the bottom, just a few model runs at a certain location for soil moisture. And we only give it the initial conditions at the beginning, and then it just runs for the simulation. Oh, and I haven't put a legend, I apologize. So in blue is the physical model, and in orange is the AI land, the machine learned model. And as you can see, they match very well. And the last year is a year that it hasn't seen yet. So even a year it hasn't seen, it's still able to capture that really nicely. And if we want to bring it back to parameter estimation, so now that we've got these more sophisticated emulators of land surface, can we actually use this for parameter estimation? And we're not quite there yet. We haven't really given it enough parameter information for it to really know what's happening in parameter space. But it is getting the right kind of behaviors, which is good. So this is looking at theta cap, field capacity. And if we change it in the machine learned model in AI land, we can see that we're getting the right kind of behaviors. We increase it, the soil moisture content increases. We decrease it, the soil moisture content decreases, which is what we expect. So it's getting the right kind of physical behaviors, which is reassuring. But we will need to give it more data about the parameters for it to be helpful for parameter estimation. And so, yeah, just to move on to the next steps. So for this offline emulator, we want to start training properly against observations to see what model biases we can learn. Like I said, use it for parameter estimation, but we need to have more parameter sensitivities. Because it's differentiable, we can use it in the land assimilation scheme, and that's also something we're working towards. And then how we're going to couple it to the Earth system components is also an active area of research. And I'm going to leave it there. So the take-home message is that parameter uncertainty is still a large source of uncertainty in land surface models. Historically, we've been using data assimilation, and it's very powerful, but machine learning is going to facilitate a lot of these, a lot of parts of the workflow, especially by enhancing computational efficiency. And then we can also start using deep learning to emulate the land surface model. Yeah, and I think that's it. And then, yeah, these are some of the citations from the talk. I can leave it there.
Thank you very much, Nina. For the audience, please put your question in the Q&A section so that Nina can try to go through them. And I would have one initial question just to trigger the discussion. You mentioned the difference, the different strategy, whether to have a different coupled small or process-based emulator, or a whole emulator that incorporate everything. What is your feeling there? I mean, in terms of traceability and also in terms of computational cost?
That's a good question. I think the problem with a big joint model, and we've been seeing that with the AIFS, is it depends what you're training it towards. And when the priority is weather forecasting, even though we have representation of the soil moisture and surface temperature, they're not the scores that have been the priority. And I think if you have separate emulators, you can really focus on making them right. And like I say, traceable, we can understand the physics a lot better before coupling them. When we have a big system, it becomes much more a black box and we don't know what's happening. That being said, if we also train everything together, we're also losing some of our biases. So we might actually be coupling things wrong, and maybe we should let machine learning discover how to couple the models. So I think there's arguments for both, but I think as a land surface modeler who doesn't want the land surface representation to get too lost in a big coupled model, I'm tempted to go more towards a joint, learning them separately and then joining them down the line. Question by Clara, will you use soil moisture observations from the International Soil Moisture Network? We have a lot in the past for calibrating. It's a great network. And yeah, I think for the offline emulator, it's one of the ones that we've been looking at as well. I think there's arguments between doing also satellite data, but obviously in situ data, we don't have the biases or the models between the assumptions that come from models from satellite data to observation. So yeah, always good in situ data. Mohammed, question is regarding emulating each part of the network, then choosing the best set of parameters. Are you using Monte Carlo simulations for each part of the network? Sorry, I'm just emulating each part of the network. So for because I covered quite a lot of things, I'm trying to understand if whether it's on the emulator side or the parameter estimation side. For the emulator, the parameters are more linked to the parameters of the machine learning model itself are found autoregressively. And then so I think we're not using Monte Carlo, we're using regression when we find the different parameter weights in the emulator. And then if we're doing parameters more in the sense of the land surface, for that, we can start using different simulations, feeding those parameters through our machine learning if we wanted to. Sorry, I'm not sure I answered that question very well. Clara, there's 10 plus years of data from the Cosmos UK, which would be a great pilot study for non-point soil moisture. Yeah, great to know. Yeah, no, I think there's a lot of data out there, which is great. Second question, so again, regarding beginners, where to start on land surface models? Where to start in the sense of to learn about land surface models or to calibrate land surface models or to emulate land surface models? I think there's a wide variety. There's some good literature. The Fisher and Coven for machine learning, I guess because it's quite an active field of research, there's not been that many. There's a lot of papers which are coming out at the moment, but there's still a lot of them are in preprints. For machine learning, for parameter estimation, we wrote a paper that's out in preprint at the bottom. It's the one at the bottom at the moment. I'm failing. There are some other papers out there as well which have come out. I will, yeah, my mind is failing right now, sorry. But yeah, maybe we can compile a list somewhere at some point. A question about the effect of updating initial conditions along with parameters for land surface model forecast. So yeah, sure. A lot of the stuff I've talked about has been parameter estimation by itself. Of course, you can do it joint. And when we're looking at web forecasting, this is quite important because on the short term, that's really where we're going to have the most impact. But when we're trying to find parameters for very long term, the initial conditions become less important. That's not to say that there aren't issues with initial conditions. One of the big issues we have is the carbon stocks, and trying to get the correct carbon stock is a big problem because it requires a big spin up. And sometimes we end up using a kind of multiplicative factor to get that right, but we know that that's not the best way to do it. But yeah, so for initial conditions, I think it's much more in the web forecasting medium range that it'll have an impact. But if we're looking at forecasts beyond that, then it is a lot harder. Question about ECLand variables that are not emulated well by AI land. I mean, to be honest, we haven't. We've been putting them in quite slowly, one at a time. So at the moment, they've been learnt quite well. It took a while to get the snow right in the AIFS, but that was just more a quirk of the model. We've been trying to put in at the moment the surface fluxes, and they're a bit noisier, so they've been taking a little bit more work to get in there. But at the moment, the behavior is very good. I mean, the main thing is with the NASFS models is that they're very much driven, especially in the short term, by the metrical forcing data. So all these land upper variables, so soil moisture layer 1 and surface temperature layer 1, they're very much driven by the forcing data. So if we can get the right forcing data, the machine learning model is really able to learn that. It's only when we get down to the deeper soil layers where we've got more memory that that takes a longer to train, and we have to get the right rollouts for that.
Okay, thank you very much, Nina. I think we went through all the question. That was a very great talk, and I would like to thank also all the attendees for the nice discussion, and see you next time for the next ML4LM webinar. Thank you and goodbye.
Thank you. Bye.